Hello everyone. Today we are going to talk about the last topic in this lecture, which is another emerging research area called program synthesis. Program synthesis is a technique to automatically generate programs from scratch that satisfy a given high-level specification. In that sense, it is a dual problem of program developing we covered in the last lecture. Okay. Today we will see two simple program synthesis algorithms and how learning techniques are used for the efficiency. Okay, let's get started. We have been talking about new techniques to achieve next generation programming systems by combining programming language and AI. Okay. Today we will cover program synthesis. Program synthesis is a technique of automatically finding desired programs that satisfy user's intent. Okay. There are many ways to provide user intent, but we will see some forms in this lecture. And given the user intent, okay, the synthesizer will search for a program through a given program space. Okay. And it will give a solution if it finds a desired one, that satisfies the user's intent. That is the whole process of program synthesis. There are many applications of program synthesis in practice. It can be used to automatically repair buggy parts of programs, or end-user programming for someone who cannot write program code. One good example is Microsoft Excel. Right? Once you give a list of examples, like this, then Excel automatically synthesizes a program that matches your example. For example, if I manually separate full name, my name, into two parts, first name and last name, then this Excel automatically captures the patterns and generates a program that slices only first name here, and in the same way slice only last name here. I guess all of you are using this feature every day when you use Excel. And synthesis can be used for software education, especially automatic feedback for student code. And another important application is super optimization. This means that program optimization, but much more aggressive than traditional compile optimization. The code on the left hand side, as you can see, is the original code that has vector extension from 32 bits to 64 bits to compute the average of two vectors. But on the right hand side here, the code is more efficient. More efficiently computes the average without this vector extension. As you can see, these two versions looks very different, and traditional compiler optimizations cannot handle this kind of optimization. So program synthesis can be used for this kind of super optimization. Another application of super optimization is secure circuit generation. As you can see, the circuit on the left hand side is vulnerable to timing-based side channel attack. As you can see, depending on the input, the circuit has different delay. A program synthesizer can generate a secure circuit that has the same behavior with the original one, but does not have such vulnerabilities. Then let's see the dimensions and design choices in program synthesis. One important thing is how to specify user intent. This is about semantic specification of the target program. There are many possibilities, such as logical formula or input-output examples, as in the Excel case, or ultimately natural languages. Another dimension is search space that defines syntactic specification of the target programs. One might want to synthesize a program written in existing languages such as C or Java or OCaml and so on. Or we can define a specially designed domain-specific language to handle a limited set of functionalities. Or a synthesizer only targets to fill a small hole in a large program. The last one is search technique. A straightforward technique is to explicitly enumerate candidate programs one by one. Or we can use some stochastic searches or advanced constraint solving techniques. But in these lectures, we are going to explore these things, okay, input-output examples for user intent, and specially designed domain-specific languages for search space, and enumerative search for such techniques. First, let's talk about semantic specification. In this lecture, we assume that user intent is specified as a set of input-output examples, so-called programming by example. For example, a user gives these input-output examples. Okay? Then the synthesis problem is to generate a function f that is consistent with this input-output set. Okay, again, given this input, okay, this one is the output of x. Okay, what is f? That is our synthesis problem. Okay, one might wonder this is a conventional machine learning problem, okay, finding a function from a given set of examples. But there are clear differences here. Compared to a conventional machine learning model, synthesized programs are more interpretable because they are written in human readable programming languages. Then it is more verifiable using conventional static or dynamic analysis. And in general, more expressive because it can support many language features such as if conditions or while loop in general. Next, let's talk about program space that defines syntactic specification of target programs. It is also very important to strike a good balance between expressiveness and efficiency in program synthesis. If you want to handle more language features, then you could synthesize more expressive program, but the search will be very inefficient. So usually we restrict the target languages as a subset of some conventional languages. For example, a restricted set of operators or control structures. In this lecture, we will consider a simple language with only two variables and without any loop, like this. The last component is search strategy. In this lecture, we will consider enumerative search that explicitly enumerate candidate programs in the search space until finding a solution. Okay? It is very intuitive and simple method. A fundamental question is how to enumerate all programs in the search space. There are two dominant approaches. One is top-down approach and the other one is bottom-up approach. Okay? But with whatever approach, an effective search space pruning techniques are needed because the search space is usually very huge. Before getting into the details of the two algorithms, let's roughly compute the size of program space with this simple grammar. How many programs can be generated whose depth is equals to 1? Okay? In this case, trivially only one program is possible with this grammar. Okay. Then how about depth 2? There are two different programs are possible, okay, whose size are less than or equals to 2. Okay, there are two possibilities. How about 3? Okay, in total, 5 programs are possible with this grammar. Okay. Then in summary, okay, this is the number of programs whose depth is less than or equals to d. Okay. Given d, we will have this amount of possible programs. Okay. Then how big is the space? As you can see, the number of candidate programs is extremely large. Okay, the search space is, as you can see, extremely huge. So effective search space pruning techniques are necessary.